Okay, so we drew the bonding structure of carbon dioxide. Now we have to find out if it's a polar covalent bond or a nonpolar covalent bond. We look at our periodic table with the dots on it because that tells me my electronegativity values. Oxygen has an electronegativity of what? 3.5, and carbon is 2.5. So a difference of 1.0. Remember we said the parameters are 0.4 and less is nonpolar. Anything greater than 0.4 to 2, about 1.8 to 2 is a polar covalent. So our oxygen is more electronegative, meaning it can attract the electrons. So our carbon is slightly positive and our oxygens are slightly negative. I saw on Pinterest a cool explanation. If, like, let's say that Ethan and I are sharing a blanket. I'm colder than he is. I hog the blankets more. So that was one of the things, one of the examples. Whatever. It's like, you know how you like share a blanket with somebody or whatever, watching a football game and it's cold. Give me that. Where is that coming from? Slightly negative oxygen will then attract the slightly positive carbon on an adjacent compound molecule. So then we're going to draw it like this. Okay. So then our question is, what are your intermolecular forces? Remember, we have hydrogen bonding. We have dipole-dipole interactions or moments, and then we also have London dispersion. We have no hydrogen here, so we definitely don't have hydrogen bonding. So here you'll have the dipole-dipole and the London dispersion. Questions on that? No. Okay, ammonia. Ammonia has 5 valence electrons. So then we're going to place the hydrogens around it. So these guys share, these share, and these share. The electronegativity of nitrogen is 3.0 and hydrogen is 2.1 for a difference of 0.9. So that means that this hydrogen is going to be slightly positive and the nitrogen is slightly negative. Right? Questions? Okay? So then either you can say this slightly positive will then have an attraction to the slightly negative nitrogen in the lone pairs. Okay? And so then we're going to have what two intermolecular forces here? We're going to have London dispersion because all covalent compounds have London dispersion, and we'll have dipole-dipole. Okay, boron tetrafluoride. We're going to have boron. Boron is one of our exceptions. It's in group 3A, so it only has 3 valence electrons. It's happy with 6 electrons, and so then we place the lone pairs around fluorine. So we have 3 shared pairs of electrons. So the electronegativity of boron is 2.0, and for fluorine it's 4.0. So it's very electronegative difference, so a very polar bond. Our fluorines will each be slightly negative. Our boron will be slightly positive. So the fluorine, the slightly negative fluorine, will then attract the boron from an adjacent molecule. Okay, and so we have our London dispersion and our dipole-dipole. What in the world is a dipole-dipole moment? What does that mean? Right, so that when they have charges, when we have 2 poles, like the North Pole and the South Pole, we have 2, it's like a magnet. Good job. Okay, and then formaldehyde, let's go carbon, 1, 2, 3, 4, because we said carbon will always be our central atom if it's present. Hydrogen can never be a central atom. We next put our hydrogens around, and then lastly our oxygen, 1, 2, 3, 4, 5, 6. Okay, so these guys will share And then to follow the octet, these will have to share. Okay? To rewrite that, you can rewrite it this way if you want. And then our bonds are going to be as far apart from each other as possible. Or it can be written, because these guys do rotate, like that. Questions on that one? Yes, ma'am. No, London dispersion is for nonpolar or polar. That's just the force, and it's the weakest force. Dipole is what shows us that we have a polar. Why? What you got? All of these intermolecular forces do. Remember, our intermolecular forces are like our Velcro holding these molecules together. Our hydrogen bonding does, our London dispersion, and our dipole-dipole interactions. These are like Velcro holding all these molecules together. And they have different strength of Velcro. Then it's our needle and thread that actually hold the nitrogens together like this. Does that make sense? Or holds the hydrogens to the nitrogen. Does that make sense? Okay, what you got? Okay, so we have an electron. We're going to do the electronegativity of the carbon and oxygen because, like I said, the hydrogen is always going to be least electronegative. Carbon and hydrogen form nonpolar bonds. So these are going to be nonpolar bonds here, and then this will be your polar bond. So carbon has electronegativity of 2.5. Sorry, 2.5. And oxygen is 3.5. So a difference of 1.0. So here you have a polar bond, right? Here you have a nonpolar. Does that make sense? Because hydrogen's 2.1. Okay, so whenever we have this slightly negative oxygen, could attract the slightly positive carbon. And so you'll have a hydrogen like this, and then your double bonded oxygen. And so right here. And these lone pairs also attract. You know, these lone pairs also attract, but in this situation, so we'll have, again, the dipole-dipole and the London dispersion here. That's kind of a hot mess, isn't it? Oh, sorry. Okay, phosphorus, I hope you kept up with me. Phosphorus is, again, like nitrogen. It has 5 valence electrons. We'll throw some 3 chlorines around it. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so here these 3 share. So we have phosphorus has an electronegativity of 2.1. Chlorine has an electronegativity of 3.0. So here, the chlorine is going to be slightly negative and the phosphorus is slightly positive. So we'll have an attraction here with phosphorus. And again, we'll have the London dispersion and the dipole-dipole. Questions so far? No questions? Okay, so water. Water is, oxygen would be our central atom because hydrogen and helium hydrogen can never be a central atom. So these guys bond. Okay, we have an electronegativity of 3.5 minus 2.1 for a difference of 1.4. So it's polar, slightly positive. This is the example that's in our homework. In our notes. So this hydrogen may attract the slightly negative from the adjacent molecule. Okay? Right. Well, it's the lone pairs that are going to be in the structure, and that's what we're going to learn today. And so this guy will have London dispersion, dipole-dipole, and hydrogen bonding. Because remember, hydrogens always want to have fun. Okay?